Kia ora Year 11 and 12. Here's question 4 from the same AS paper that I've been going through. This one's a geometry question, and I've chucked the picture or diagram onto the front page here. So when you see that, you should hopefully see straight away 3 sectors, and that should make you think about an area of a sector formula, right, which is half r squared theta, and also maybe the arc length formula is going to come in handy here, and that's S equals r theta. And this is even before you've really read the question. The other thing to notice on that diagram is that this angle here is theta. We've got this little sector here, so we're going to need to have this angle in here. And that's going to be pi minus theta because of angles on a straight line, adding up to 180 degrees or pi radians. So now let's have a look at the question. We've got a metal plate, and it consists of 3 sectors, as we saw, each with centre O. The radius of the big one is 2r, and the angle is an easy theta, and the radius of the other sectors is r. And we've already figured out that this angle here is pi minus theta. So we have to find the area of the metal plate and show that it's equal to this. So the area is going to equal the area of the big sector plus 2 lots of the little one. Now I'm going to do this all in one go because it's quite a straightforward expression to write out. So we've got a half, and the radius here is 2r, so a half times 2r squared theta plus 2 lots of a half r squared, but my angle here is pi minus theta. Now if that were a more complicated problem, I'd do these 2 separate bits and then put them back together, but this one seems fine to do like this. So we've got a half times 4r squared theta plus r squared pi minus r squared theta. So I'm just expanding that out. That gives me 2r squared theta plus r squared pi minus r squared theta, which is r squared theta plus r squared pi. And I'm going to rewrite that in the order I'm asked for, so it's r squared into pi plus theta as required. So there we go, there's the first bit done. Now the perimeter, we have to show that it's independent of theta. To find the perimeter, I'm going to use the arc length formula, but don't forget that the perimeter is not just these arc length bits. It's also the other edges, the straight edges of the metal plate. So it's really easy to forget about that and waste a bit of time until you've realized what you've done. Okay, so let's now find the perimeter. And if you remember the arc length formula, this is a really easy question. So we've got C, actually we'll make it P for perimeter. So it's equal to the 4 straight line bits, so 4r plus 2 lots of these little arc lengths. So this has got a radius of r, but the angle is pi minus theta. And then we've got one big one, so this arc length is subtended by an angle of theta, but the radius is 2r. So it's going to be r, the radius, which is 2r, times theta. So if we put all that together, we get 4r plus 2r pi minus 2r theta plus 2r theta. And we've got leftover working from the question above there, never mind. And you can see that that cleans up to give you 4r plus 2r pi, which is independent of theta. So there you go. I think that's a pretty straightforward 4-mark question. Hopefully what this question shows you is that you need to be really confident with the basic formulae. I know you'll get them, I think you get them on the formula sheet, but you should have done so many problems that you don't need them. The other one that we're missing in here that we haven't used is the area of a segment, which is a half r squared theta minus sine theta. So this is also extremely useful, and I often remember that from a proof, which is that it's the area of the sector minus the area of the triangle. So they're your main ones. And lastly, always work in radians. Alright, this is pretty short. I'm not going to do the vectors question in the same video. I will keep that for a separate one, but that's coming up soon. Thanks for watching.